Okay, good evening. So today's lecture is on neural networks, part 2. We covered biological motivation of neural networks last time. Why these neural networks exist, why are they called neural networks, and so on. Today we'll actually look at the preliminary formulation, the mathematical formulation, which is a whole set of functions. And we refer to the kinds of models we look at here as feed-forward functions. You have inputs and that are carried forward through neurons to perform some computation that we're interested in, to compute a function. Basically, a neural network computes a function f of x. X is an input, which is not just a scalar, but maybe a vector, maybe an array, like it could be not just a one-dimensional vector, but a two-dimensional array of values of pixels on an image, or it could be three-dimensional where we have, let's say, 3 dimensions of red, green, and blue, which means 3 layers of arrays. And we might have a video as input, which makes it a time sequence of a sequence of three-dimensional arrays, which is why we refer to X as a tensor. So the job of a neural network is to take a tensor X as input and compute some function. The function could be just a value, or the function could be a binary decision, yes or no, or it could be the probability if it's belonging to one of several classes. Or a neural network can also be regarded as a generative model where it is capturing the distribution of the data from which you can generate samples of the distribution. So these are all the kinds of things you could do with neural networks. So what we're going to talk about today is what are called as network functions. Right? To compute that function f, we also use along the way some activation functions, right, which takes a set of inputs and multiply them by their weights and adds them all up together. It's a vector multiplication, which is W transpose X. X becomes multiplied by W transpose. And that quantity is a scalar quantity, W transpose X. It's a vector multiplication, but that results in a scalar. We input it to an activation function such as sigmoid or a hyperbolic tangent, or there are so many variants of that. There's what's called as a rectified linear unit or a ReLU, or it could even be a soft plus function, which is a soft version of the ReLU. So on, there are so many possible activation functions. We look at those activation functions, but then we look at also the inputs are not just x's, but phi of x's, some features of the x's. Phi is the Greek letter for f, or feature. So it's the features phi of x. And what are those features? The features could be selected manually to be something like a set of Gaussians, which are called basis functions, Gaussian basis functions. That network, such a network is called a radial basis function network, RBF network. And so we'd say, well, you've got these hundreds or thousands of input features in X. We don't want that many. We are going to use some set of basis functions to map. We take a high dimensional input and we produce a smaller number, phi1 through phi m of x, and there will be only m values. M is a much smaller number than the initial dimensionality d. So who specifies those feature functions? We could say, well, we specified, we give appropriate basis functions like Gaussian. That is the approach of a class of methods called support vector machines, SVM. You select a set of feature functions. And the cleverness of SVM is to not to use all of them, but use a subset of them. And so, this phi of x, phi1 through phi m of x is also a vector. And it goes about selecting a subset of them. So selecting only those that are necessary to do the classification. If points are too far away from the supporting planes, then we say, look, there's no point in keeping those. And just keep the ones that support the separating planes, for example. And so those methods are called as support vector machines. That's one approach for computing these functions. The other approach is the neural network approach, where the phi functions are not selected as such by the designer, but they are actually computed by another network. So we say we have a function of a function. So we want to compute a function, yeah. But this says along the way, let's use some feature functions, which are going to be computed from the raw inputs. And how are those functions computed? Well, those functions behave exactly like the overall linear function. And that consists of a bunch of weights, and you multiply the inputs by those weights to get a smaller set of features. And those set of features are then given to the final decision step, right? So that is the idea of these linear. So these are all still linear models. Each layer is linear. And so we take linear functions of linear functions of linear functions. So that is what we do here in neural networks. It's interesting that they work very well, these neural networks, even though they're only linear in the input. They can do amazing things. Deep learning can do amazing things. All the fancy things we're talking about today, all the, the autonomous vehicle driving methods, or any of the fancy things you see, any of the fancy things you use every day is AI, right? Anytime you go to Google and you ask a question, it's figuring out exactly what you want and using AI and machine learning to come up with the answer for you. And all of that is based on linear functions. Linear and linear and linear, maybe several layers. Those are linear functions. But yeah, here is an example of a topic that is one of going more into depth. Turns out that this linearity built into neural networks has a drawback in that they become extremely sensitive, and it is possible to actually create certain types of noise and add it to your inputs, and that will make it behave in a bizarre way. So while they do very well on training sets and testing sets and so on, if there's called adversarial inputs. If you create some adversarial inputs and feed it to a linear network, it'll get the answer completely wrong. So that's a whole area, adversarial training of neural networks. Anyway, we'll talk about all those. So the big picture for today's lecture then is uh, these functions, how are they defined? Going from input to output, and the feature functions, how are those defined? All linear, nothing very new there. And of course, difference between SVM and neural network. And also the activation functions. Those are, things like, Sigmoid and tanh and ReLU and Softmax and things like that. So our topic is mainly just looking at all these functions. We will say, how is regression accomplished? We can do regression with neural networks. How is regression accomplished? How is binary classification accomplished? That's the logistic regression style of things. The binary classification can also be done by a neural network, although logistic regression is designed for it, but it doesn't have any feature functions built into it. So when we bring that in, it becomes a neural network to do binary classification. And then multi-class classification. We just don't have 2 classes, but we have 10 classes or what have you. and for which we generalize the idea of a sigmoidal function to a softmax function. So all of this, so we want to get familiarized with these kinds of functions, the overall functions and the activation functions and sigmoidal and softmax, so a whole bunch of functions. All right, so that is mainly. So today we won't talk about computing those weights. That's going to be done in the next class. Today we just familiarize the functions, and we'll simply say, well, the functions all involve using a set of parameters. And how do you figure out the parameters is the subsequent topic. So today we won't look at that part of it. Okay. All right, I'm going to now share screen with my slides, which is 5.1, which is feed forward network functions. All right, I just double clicked on it. I hope that automatically brings you into slide share mode, or right? So I hope you are able to see that. And I'm going to put it into slideshow mode. All right. You can holler if you cannot see my slides. Okay. Anyway, it's available online also for you. You know, you can also look at it online, either in at UBlearns, or you can look at my public site. Here is feed forward network functions. Those of you who might be downloading some of these slides early on, you may want to re-download it, because what happens is on the day of the class, I end up looking at those slides myself, and then I try and say, oh, okay, I could do something better than that. So I update it a bit and so on. So you may want to look at the latest version. All right, so what are the topics here? Extension of linear models, feed-forward network functions, that is the main thing. Activation functions, overall network function, weight space symmetries. Okay, so this is all looking at the neural network, what all it involves. So look at this one function. It's a general form. Linear regression, linear classification can be expressed in a simple way like this. It says y of x comma w. X is the input, y is the output, w is a set of weights or parameters. And that is nothing but a function f of summation wj phi j. So the x's are all subject to some phi j's. These are the basis functions, and there are m of them, j equal to 1 through m. And we weight each of these and add them up. It's a function of that, and that is what your scalar output y is. Where x is a d-dimensional vector, phi j of x are fixed nonlinear basis functions. Example, Gaussian, sigmoid, powers of x, what have you, it can be anything. And regression f, for regression, supposing you say, well, how does this equation allow me to do regression? Regression says get rid of this f in this formula. So f is the identity function. So regression would be just wj's vj summation. That's it. Some value you're going to get. F is the one that kind of is mapping into what you're interested in. If you are looking at classification, I want an output of 0 or 1. That f can be the logistic regression function, where it is defined as f of input a is equal to 1 over 1 plus e to the power of minus a, which gives you a value between 0 and 1. Essentially, that will give you a probability as output. It will say 0.7. Y of x comma w is equal to 0.7. Of course, we'd have to define, what do you mean by that? For a binary class problem, 0.7 is the probability of 1, and 0.3 would be the probability of 0. That's a two-class problem, and it's giving you a probability over here. Where it's giving you a probability, how do you figure out this Wj? That comes from a maximum likelihood formulation of probabilities of a Bernoulli function and so on. And that is how we maximize the probability for a data set. And that's how we figure out the W's here. All right. So that is a very general formulation. Of course, we have to mention the multi-class problem also, where we can use the same thing. We'd compute several of these for each class, and then we'd normalize them using Softmax. So that you can do generalization. Okay. Fixed basis functions, when you have fixed basis functions like this, have limited applicability due to curse of dimensionality. So in the sense, if this is a very large number of dimensions, number of coefficients needed is large. Means of Gaussians that you're going to be using here grow with number of variables and so on. So fixed basis functions are have somewhat of a problem. To extend to large-scale problems, it is necessary to adapt basis functions phi j to data. So we're saying those phi j's should be derived from the data x. So that's what a neural network does. It figures out what are these feature functions phi j. So they become useful in large-scale problems. Both SVMs and neural networks address this limitation. SVMs say, instead of using all of these phi j functions, use some subset of these m, and those are the support vectors we're going to be using. And how to select those support vectors is what SVM does, which will come as a later topic. So today or for the next few lectures, we're dealing with neural networks. So SVMs and neural networks address dimensionality limitation, and we refer to this as a generalized linear model. The SVM solution is to vary the number of basis functions m centered on these training points. Select subset of these during training, and the advantage is although training involves, this involves nonlinear optimization. The objective function is convex. Okay, so objective function for the SVM problem, how are we going to figure out the support vectors? The solution is straightforward. So it's a convex problem, right? We got an optimization, which is a bowl shaped. So we find something to minimize it. And number of basis functions is much smaller than number of training points, although large and grows with size of the training set. So the number of basis functions is much smaller than the number of training points. We're now relating it to that. But the one approach is to center all of these phi j's on the training points, Gaussian on all the training points. SVM says no, we can more cleverly select those points. The neural network solution, number of basis functions m is fixed in advance. But yeah, so with a neural network, we got to say the number of functions is going to be fixed in advance, some number. That's the hidden units, for example, in a neural network. The inputs, of course, is the raw inputs. And m is the number of hidden units. So that is the number of basis functions. And allow them to be adaptive, but the phi j's have their own parameters, wji's. So we would have the phi j's, which are m in number, have their own parameters. This is the parameter of the overall function, these wj's. We'd have to have some more parameters for the phi j's. Adapt all parameter values during training. So instead of y of x comma w is equal to f of summation wj phi j of x, we have yk, supposing we have a k class problem. Kth value of xw is equal to sigmoid wkj, and then there's a h of wji. So you see the inner loop here corresponds to computing the features, the inner loop, h of wji xi. So d is the number of dimensions of the feature, and it is producing a set of m hidden units values. The reason h has been used here, I suppose, strategically, h for hidden. The output is the usual sigmoid here. So this h also could be a tan h function or a sigmoid function. And then you see there's a bias term here, and then you see this wkj times input. This is the phi j of x here. And then there is a wk naught. So there's a recursion here into two levels. Of course, you can say, we could do this again, couldn't we? Just like you had wkj, there's wji. What about this wji? Well, I could say we could do one more level here, and that would be nested 3 times over. We would say that's a neural network with 2 hidden layers, or we could recurse as many times as we want, and we get a deep neural network, which would be this inner loop produced with inner, again and again. Okay, so remember that a neural network is a function of a function. The input x, we compute some values here, h, and then we compute another function. So it's a function of a function. We say that such a function is a composite function. All right, so we have something to keep in mind because those things become important with neural networks. Oh, we have one more slide on SVM versus neural networks. So who uses which? Supposing you're just a user of machine learning, you're not a committed machine learning, researcher, or that's not your end goal in life to do machine learning. Just use, okay, I need to solve this problem. I need a method to do some either regression or classification. So SVM involves nonlinear optimization, and objective function is convex, leads to straightforward optimization, single minimum. There is no issue of dealing with global and local minimum. And the number of basis functions is much smaller than the number of training points, often large, and increase the training set. There is a variant of SVM called RVM, Relevance Vector Machine. So it's a Bayesian, all of these things, there's a Bayesian versions going on. First, we discussed the main method, and then you say, couldn't we do it in a Bayesian way? And that's a straightforward question to ask. It doesn't require that much thinking to say, what would be the Bayesian version of the problem? Bayesian version says, we have some prior knowledge we want to incorporate into the problem rather than everything to be learned from the data. So we would have, if you need weights for the network, all right, we'd have a prior distribution of the weights. And if you do that with an SVM, it becomes a relevance vector machine, produces probabilistic outputs at the expense of non-convex optimization. All right, so this is, that's about SVM, which is a later topic. With neural networks, there is a fixed number of basis functions, parametric forms them, parametric in the sense there's a whole bunch of values. And then multi-layer perceptron uses layers of logistic regression models. That's what it is. Logistic regression, which we emphasize so much, it's the basic building block, if you will. It's like you're trying to build something out of Lego blocks, So in this case, each Lego block is logistic regression. So we are just piling up logistic regression on top of each other. And there are certain rules of how the Lego brick is connected to another Lego brick. And you can create all kinds of deeper networks. And okay, so that's a neural network, and also involves non-convex optimization during training. And it's not convex optimization. In that, non-convex means there are multiple minima. The objective function is non-convex, we say. When you say the objective function is convex, it means it's something like the shape of a bowl is convex. It's a convex shape. Non-convex means there are all kinds of ups and downs and so on, hills and valleys. That's a non-convex. So it has many maxima and many minima. And at expense of training, so it requires effort to train a neural network than SVM. And we get a more compact and faster model. So we can do that. All right, we already saw that origin of neural networks. It's the information processing models of biological systems. But keep in mind that we discard too much of biological realism in discussing this discussion of functions. And because otherwise it might impose unnecessary constraints. We're saying, well, that's not how a neuron works. Well, it's got all these things about, temperature and whatnot might be coming into play, which we don't worry about those kinds of things. Anyway, neural networks are efficient models for machine learning, particularly multi-layer perceptrons. We saw what a perceptron was. These are multi-layer And the parameters are obtained using maximum likelihood. So how do you get those values, WI? We get it using maximum likelihood, which means we formulate the problem probabilistically. So the use of probability theory becomes absolutely essential in designing machine learning algorithms. So the outputs are probabilistic, right? Probability is between 0 and 1 for the classes. And given a set of samples, we end up having a underlying probability distribution with some parameters. And then we say we need to choose those parameters that maximize the probability of observing the data set that you're given, which is called as the likelihood. So, and then we figure it out such that it maximizes the likelihood. Maximizing the likelihood becomes minimizing the negative log likelihood. And that is essentially the cost function. So the maximization saying, okay, you got to maximize that or you got to minimize that, which means we have to do gradient descent on that maximum likelihood function. And so we need to compute derivatives of that. So anyway, that's, and then computing derivatives is a complicated matter. And there is a clever algorithm for it called error back propagation, which computes that efficiently. So again, this is the general feed-forward network function. That's such a simple function. And these are the basis functions. And this is an activation function, we say. For regression, it's the identification function. For classifications. So what is that F? That F is just a activation function. So there are activation functions inside, there are activation functions outside. And so that is, so we need to examine that part of it. So the basic neural network model can be described by a series of functional transformations, D input variables x1 through xd, M linear combinations of this form, and superscript 1 indicates parameters are in first layer of network. Parameters wji1 are referred to as the weights. Parameter wj01 are referred to as the biases. X naught would be one additional input, which we take it to be equal to 1, in which case we can get rid of this term if X has one more term in it. Quantities AJ are known as activations. Oh, so it's been chosen carefully. W for weight, D for dimension, M for number of model parameters, A for activation. All right, so they're all very strategically chosen names here. So A are activations. Number of hidden units M can be regarded as number of basis functions, where each basis functions has parameters which can be adjusted. So what kind of activation functions can we choose? And each activation AJ is transformed using differentiable nonlinear activation functions. So ZJ correspond to outputs of the basis functions. And that takes as input some activation and it produces, I guess, it's how the activation input becomes an input to this activation function to produce the output. Okay. So that is, we can say that is the activation, this is the activation function, this is the activation input, right? We need to straighten our terminology here. Then these are nonlinear functions H. So they bring in nonlinearity. Although we have all of this linearity in, we keep on saying linear classifiers and all that, everything is linear, but more complicated things are accomplished by having nonlinear activation functions. Examples of activation function are logistic sigmoid, which is defined as sigma of A is equal to 1 over 1 plus e to the power of minus A. We've seen the shape of that thing. It's an S-shaped function whose value lies between 0 and 1. And there is the hyperbolic tangent, which is kind of a relative of sigma of A actually. Anyway, it's tan hyperbolic A is e to the A minus e to the minus A, e to the A plus e. Why use this hyperbolic tangent? Is that this value lies between -1 and +1. So sometimes in some formulations, that is a preferred formulation. And if you want that formulation, -1, +1, with the in-between value of 0, this would be between 0 and 1 with the in-between value of 0.5. So that's hyperbolic tangent. And then today, the most used activation function is the rectified linear unit, or ReLU, which is defined as max of 0x. So you give an input at x, and it says it simply outputs the x if it is positive. And if the value of x you give me is negative, it simply outputs the value 0. So we can say it's max of 0x. It's kind of a discontinuous function, but it turns out to be very powerful from the point of view of learning. Learning is all about computing derivatives. So computing this derivative is going to be very simple with x. This derivative also you can use the derivative. The reason we choose sigmoid and hyperbolic, they are continuous functions whose derivatives have simple analytical form. And one more function you come across as an activation function is called soft plus. This soft plus is input A. It counts, I guess, zeta. Zeta. That's the name of the hurricane coming to the United States right now. They started naming all those hurricanes by Greek symbols. They ran out of names of people from A to Z or A to Z. So they started naming the hurricanes alpha, beta, gamma, delta, I think epsilon. I think this is the one that comes after that is zeta. Zeta A is equal to log of 1 plus exponential of A. Turns out this is also a relative of sigmoid. If you take the derivative of this, d by dA of this quantity is exactly equal to this. So these are all not, this is like a very nepotistic family of relevant functions. They're all kind of related to each other. Not a huge difference between logistic, sigmoid, hyperbolic, tangent, soft plus, and some kind of a discrete version of soft plus becomes rectified linear unit. So this looks like a rectified linear unit. So second layer activation. So again, the same idea is repeated one more time. Values Zj are again linearly combined to give output unit activations. And so this is nothing new here. So activation for regression classification determined by the nature of the data. For standard regression problems, the activation function is identity. So we don't have a sigmoid at all or a ReLU at all for regression. So we just simply add them up. That's it. Well, what about, there is no Bernoulli type of assumption? The maximum likelihood is formulated in a different way for regression. We talk about this output of a Gaussian, and we use such a model to define the loss function, which turns out to be equivalent to minimizing the sum of squared errors if it is a Gaussian noise model you're using. Whereas for binary classification, we use Bernoulli, and we generalize it to multiple classes using Softmax, which we see. We'll try and define Softmax clearly. So this then is the equation for a neural network. Look at that, where we have ended up with. We started out with the biology of the brain. We said the brain has 10 billion neurons connected up. We saw what the photograph looked like. We're saying, okay, we have modeled, this is just a model, right? We have a model how the neurons in the brain work by this and by this picture. These are the inputs coming in here, coming from the eye, maybe the retina of the eye, and they're multiplying all these by weights and create these values in between, and we multiply them by weights, create these outputs here. Let's recognize it's a dog or a cat with all these probabilities here. So I suppose this whole thing becomes your cortex, cerebral cortex here. And what is this? This is going to some part of the brain telling you what it is, right? Inputs are the, anyway, so there's the analogy. And the whole thing modeled by this simple equation, which says the yk, this kth value of the output is a sigmoid here. This is a sigmoid, a value between 0 and 1 over here. And that value is a sigmoid of a quantity where we're multiplying these weights, the second order weights here. And these again, the values over here again are computed by another activation function h, which is all these weights here, multiply these xi's, and you have this, right? And then these biases are being modeled as, this is always one, it's filled in node. This kind of terminology of probabilistic graphical models, when you draw a model like this, if the node is open, it means it can be any value. And if it is closed, means we know the value. So this is known to be 1 and known to be 1, in which case we can just change the d to d plus 1. It's not just d inputs, but d plus 1 inputs. This input is set to 1, which means we don't need this term w naught term here. So this is, these are the values. So every one of these outputs is coming out as a value between 0 and 1. This might say that's a 0.9. And this might say that's a 0.8. Oh, wow. What is it? They're not adding up to 1, 0.9 here and 0.8 here and a 0.6 here and a 0.5 here. Well, you know, it would be nice to normalize all of them. And that's what Softmax does, as we see in the next slide. So this says, what is Softmax? Softmax says if your network output is 1.3, 5.1, 2.2, 0.7, 0.1, these are all the various values that have come out. Then the activation function Softmax says take these values, each of them, the ith value here, raise it e to the power of that, and then divide by summation over all of them e to the power of all the yj's, the summation over j, we say. That comes out clean. Comes out as a probability 0.02, 0.9, 0.05, 0.21, and all of them add up to 1. And you see the 5.1 became 0.9 and 0.7 became 0.01. So it is kind of telling you, so we refer to this as softmax because it is telling you in a very clear way which is the maximum of this. It's telling you that this value, second value, is going to be the maximum. And that's, that is it. And it says the second highest value is what? It says one with the score of 0.05, I suppose, which is 2.2. Yeah. And the third one is like that. It's telling you the ordering of all of these. So, but it's all normalized, giving you a value between 0 and 1. So that is why it is referred to as softmax. So the network is outputting all kinds of values here, which are all being nicely done. If you had only 2 classes and not 5 classes like here, this whole thing would be equivalent to logistics sigmoid. 1 over 1 plus e to the power, it becomes the same thing, okay? So softmax is a generalization of sigmoid to many values.
Professor, sorry to interrupt. There's a question by Argya. The question is it necessary to have the dimensions of hidden layer vector equal to the feature vector dimension?
Okay, I'm not sure I got the complete question. Let me repeat what I think what it is. Is it necessary for the number of hidden units to be the same as the number of input features? No?
Yes.
No, obviously not, because we are trying to always, get rid of the curse of dimensionality. We're having too many inputs. So, the X could be your megapixels on your camera. We don't want to be dealing with such a large number to recognize whether it's a cat or a dog. We want to quickly reduce it. X could be a 1 million megapixel is 1 million pixel, 1 million values. we want to go down to some, maybe few, in the beginning, maybe a few hundreds, few thousands, and then with another layer, few hundreds like that. If it is a two-class problem, then we quickly want to reduce it. So typically, the input is d dimensions. The input has d dimensions here, which is a big number. And the number of hidden units, m, is a dramatically reduced number. So we had d here and m here. See, d is, so typically m is a smaller number. Although in this diagram, it looks like it's becoming bigger. Maybe that's the confusion, but it is smaller number. Does that answer your question? You can speak up. Okay. Right. So these deep learning networks, that's what they do. They start with something with high dimensionality, and they keep on layer by layer by layer by layer, they're reducing it. What they're doing is at each layer, it is figuring out some essential features of the object to be able to go to the next one, to go to the next one, to go to the next one, bringing it down to some essential features. And of course, what is driving, how does it figure out what are the features? That's called the representation issue. That representation is to some extent done by the back propagation we do, saying, okay, you figure it out, what are the things that are needed, and so on. It keeps on. And then there are also all kinds of things goes on in between. The convolution neural networks kind of reduce the number of operations needed and all that. And the pooling operations further reduce it and so on. So there are all kinds of things going on in between. But mainly, this is the process of neural networks and deep learning, which is just many layers of these. Okay. All right. Yeah, feel free to ask these questions, because sometimes I kind of move on thinking, okay, that's obvious, but it's good to get some interrupts and saying, okay. And unfortunately, I do this on a laptop, and there is no indicator that you have. Yeah, maybe I should try. There must be, even on a laptop, I should be able to. I can't see the panel because also I'm on full screen mode, which kind of hides a lot of stuff. So anyway, thanks Mahir for prompting me the question. All right, so then we go on to do some very simple things here. I'm wondering whether I should ask you to read on your own or no. I guess we have some time. Let's go over it. Sigmoid is the softmax function here. Sigmoid is a softmax is different. Sigmoid goes from 0 to 1. And look at that, it transitions. It's good to know what the sigmax is. Sigmoid is a very simple function. Sigma of a is equal to 1 over 1 plus e to the power of minus a. That function behaves like this. It goes from 0 up to, when it reaches around 0, it starts going up and up and up. And then it becomes 1. So it's called a squashing function. It takes any input a. If it's a very big input, then the output along the x-axis, if it's any big input, the value is 1. So it's a negative value, value is 0. Somewhere in between, it's got a smooth transition like that. Softmax, as I said, is a generalization of this. You've got several of these sigmoids which are generalized. All right. Where, see, this one took AK as input, sigmoid. Each of these exponentials take AK as input, several of them, that's all. In this case, there was only one of them in this sigmoid function. This is several of them. So a choice of for network trading, all right. Tan H is a rescaled sigmoid function. Is a rescaling of the logistic sigmoid. So the output range from -1 to +1. Look at that, -1 here, and it goes up. And you see this blue function is the sigmoid, which is kind of, when you have the scale is expanded, it looks not so interesting, right? It's kind of just making a small transition here, whereas this tan H seems to have a more pronounced appearance, which is kind of an advantage, that the region of nonlinearity here is larger. So how do you define tan h? Tan h is nothing but 2 sigma 2a minus 1. It is just a version of sigma of a. It's a scaling of it. But that turns out by doing some algebra, that is exactly the same as tan h of a is equal to e to the power of a minus, that's this. The output range -1 plus 1 is more convenient for neural networks. Aha. You see, if you are going to be a brain modeler, we said the neurons in the brain have inputs coming from other neurons, some of which are excitatory and the others are inhibitory. This nicely models that and says negative means inhibitory, positive means excitatory, and it's figuring out the total of all of those. So it seems to be a nicer model than just sigmoid, and it is also continuous. It is differentiable. All right. So there is the tan h. This is the surprising emergence in last, maybe 5 to 7 years or something of a rectifier linear unit, f of x equal to max 0x, and where x is the input. So that function looks like this. It is this black function here. It's at 0 here and then goes off as a 45-degree line from this point, which is the value of x. Input and output are the same. Okay, so f of x equal to max of 0x. So when you give me an input x that is negative, it's going to output 0. When you give me a value positive, it says, okay, that's the value. That's exactly the same value, max of 0x. Where x is the input to the activation function, this is called a ramp function, ramp. And argued to be more biological than widely used logistic sigmoid and its more practical counterpart, hyperbolic tangent. It can be argued that this is actually the kind of output. It is not going to 1. Previously, it was going to 1. And this is saying, no, just keep on increasing this. It's a popular activation function for deep neural networks since function does not quickly saturate. So this becomes a serious problem when you have multiple layers because we're going to be computing derivatives. And when you have a function that is kind of flattening out from 0 to 1, it's a very flat function. And what is the derivative of a flat function? 0. Although it might be very infinitesimally reaching 1, 0.99, 0.99999, 0.999999, so on. But the gradient of that function is going to be so small. So for all practical purposes, there is nothing, 0, derivative is 0. When derivatives become 0, you cannot update your weights. That is the whole crux of machine learning is updating those weights because you're learning from the data. Fine, mathematically you said you can do it, but practically speaking, the precision with which you can represent those 0.99, 0.9999 is limited. So it's all going to be just essentially zeros, and so no learning goes on. So for when you have multiple levels of layers in a network, sigmoid is not the right thing for practical considerations. So we say, okay, use ReLU, rectified linear unit. The word rectifier comes from an electrical engineering term. When you have an input signal that is, for example, you have alternating current, right? Like you have the voltage can, go from positive to negative like that, right? So uh, you have sinusoid shape of the voltage, alternating current. And batteries, on the other hand, are direct current, right? So batteries give you a constant direct current, whereas generators that generate electricity from Niagara Falls, right? They generate alternating current, which goes positive, negative. Actually, originally, Thomas Edison wanted Niagara Falls to be generating direct current, just like your household battery that you use in your laptop or on your whatever flashlight or the car battery. They're all direct current generators. And Thomas Edison wanted Niagara Falls to generate electricity using direct current. But it turned out direct current doesn't work very well when you transmit it over a long distance. If you want to transmit over 10 miles or whatever, to transmit power from Niagara Falls to Buffalo, which was the very first electrical transmission in the world, they couldn't do it with direct current. So they needed alternating current, positive and negative. And when the electricity reaches Buffalo, you want to use it to as direct current to power things, and then you use a rectifier to convert into a direct current, which converts it into a constant positive voltage. So we call it a rectifier. Same idea. Anyway, long story about a rectifier in Buffalo. Our rectifier is converting the negative values to 0 and positive values keeps it. So it doesn't want to look at negative values. It's keeping them as 0. So in a way, it's a rectifier. And also it's a rectifier here, and then it's a linear unit. So it's called ReLU. A smooth approximation is log of 1 plus e to the power of x. So it turns out there is another function here, a smooth one that comes like this and smoothly goes up like that. It's going to be a differentiable function. This ReLU is not going to be differentiable at this point 0. It's not a continuous function. No derivative exists. There's a derivative throughout here. Derivative of x is equal to x actually for this function. And this smoother one will not have that issue. And the derivative of soft plus. And what is the derivative of this soft plus? It turns out to be logistic sigmoid. 1 over 1 plus e to the power minus x. So this function here is related to sigmoid. Sigmoid or logistic sigmoid. Same thing. And we saw tan h is related to it. ReLU is also related to it. So these are our favorite little functions that goes into our brain and that goes into artificial intelligence. Comparison of ReLU and sigmoid. Sigmoid has a gradient vanishing problem as we increase or decrease. Yeah, sigmoid has a problem. See, look at the sigmoid is this green thing here. There is no gradient in these values. If the input you give is any of these values, it says 1, 1, 1, 1, 1. There's no change. No gradient equal to 0. Whereas the max 0x, that is this blue one, has gradient as we said is x, and then the red one is a log of, that is the softmax, that has also. So look at these functions that are very distinct and going up, whereas this one has squashed it all between 0 and 1, which becomes useless for the purpose of deep learning. But it's okay for one layer, hidden layer, a neural network. It should work just fine because you might be in this zone where training is possible. Functional forms of various activation functions. I found some nice one here. Sigmoid, the function, what it looks like. There is a tan h here, and then ReLU here, and then leaky ReLU. This is another one, max 0.1xx. That's interesting. Leaky ReLU. It says there is something going on the negative side also. Max out. This is a popular one. You'll see people will say, I used a max out network. What? What is max out? Well, max out is W1 transpose X plus B1, W2 transpose X B2. It is taking the max out of two linear quantities here, all right, two values. Well, where do the two values come from becomes the question. So maybe two outputs or something. So anyway, there is one function like that, max of these. Right. So it's not very clearly explained how it's analogous to all of these. I suppose it is. You take X, there are two sets of weights here. Two sets of weights multiplying them. This is the raw input and this is the weighted output. LU, wow, what is that? It's something like this. Anyway, isn't that interesting? That there are so many variants that are possible when you're trying to implement even a simple neural network. And what about derivatives? It's nice to have a table of all the derivatives, because if you're going to be implementing derivatives, because you're going to be computing the derivative to update your weights, Remember, gradient descent involves Wt plus 1 equal to Wt minus eta times derivative. So it's along the way, one of the things you have to compute derivative of is the activation function. So it is saying for each equation, let's say for hyper tan inverse x arctan, I guess for that one it is 1 over x squared plus 1. For soft plus, we just saw that soft plus, it's same as sigmoid here. And ReLU, we mentioned it is if prime f x equal to 0 or 1. I was saying x, it's actually 0 or 1. Derivative with respect to x of x is equal to 1. It's not x, it's just 1. I was saying, I misstating it earlier on. So that's it is saying your derivative of your function is 1. How much simpler could it be? If you're going to be doing chain rule of calculus and all that, that's going to be turning out as 1. Right, so this is, and there are so many others here, right? So there is a whole bunch of stuff. So we saw the overall network function. Okay, this is just a repeat. There's nothing new here. Forward propagation. We refer to this thing as forward propagation, going from left to right as forward propagation. Going from right to left is called backward propagation. That's what we need to do to compute derivatives. So feed forward is like this. In general, some of the math we're talking about can be applied to general feed forward topology. It need not be layer by layer by layer, and we could jump layers, skip layers. There are certain networks that do that. Skip layer and all that. ResNet or something it's called, right? So it takes an old value as input, and this applies to that also. Examples of neural network models of regression. So this is showing how the hidden unit values together conspire to compute the function. So here we have a function. Let's say the neural network was simply to compute f of x equal to x squared. Nothing fancy, nothing like recognizing faces. Just give me the x squared value. Neural network to compute x squared. Let's say you're programming a calculator. You want it to compute x squared. And you give inputs as x and outputs as x squared, and it learns it. Then x squared has this behavior. When it's negative, it is positive output. When it is positive, it's positive output. 0 at 0. That's what f of x equal to x squared. If you used 3 hidden units to compute that, the 3 hidden units together are these 3 dotted curves. Together, their values add up to give you this. The weighted addition of those things gives you that. Similarly, sin x is this. Sin x over here is added weighted addition of these 3. And this is f of x equal to absolute value of x, which is this kind of a function. That again shows you what the hidden values look like, hidden units. And you can get a Heaviside step function, 0 and 1 like that. That also has got, look at this component here, some dotted line coming like that, and together they're gone. Yeah. Mihir, how are we doing on time?
We can start in the quiz in like 5 more minutes.
5 more minutes you give me, okay. All right.
So there's one question by Vineet.
Yeah, go ahead.
So the question is, if the values for the gradient are 0 in ReLU, wouldn't the learning stop at that point?
Yeah, that is an excellent question. You see the squashing happens, this is in sigmoid. What's happening in sigmoid? That is also going to a squashed value, right? So at negative values, it is squashed to 0 with sigmoid. And we are essentially squashing it to 0 on this side. Now, the positive side, we are, of course, generating gradients. So on one side, it is behaving just like the other one. That is why they've come up with this leaky ReLU and things like that. And of course, the question to be asked is, shouldn't it be symmetric? I suppose we're taking advantage of converting things to being on the positive side with ReLU, all right? So we are giving advantage to one side. I suppose the training is done so that we are exploiting that situation. It is not necessary to have minus X also. Okay. So it is just positive values rather than negative. Okay, good question. So this ReLU was an interesting development. I've been teaching this neural networks, machine learning for decades. There was no ReLU until about 5 or 6 or 7 years ago. Suddenly it's burst on, and that is the way. But still, sigmoid plays a role all over. But ReLU is handling this vanishing gradient problem. All right. So the output is linear with the input for a positive input. On the negative side, there are some small variants of it. That's why you have some of those other inventions. Good question. And so the answer is not perfectly clear, but you get a sense of it that it can be managed on the positive side by appropriately dealing with it. Okay. All right. Is there any other question? So, you see, when I did these lecture slides, there was no ReLU. We didn't know about ReLU when I did. Actually, my slides on these go back to Chris Bishop's book, which is about 10 years old now. There was no ReLU. There was no mention of ReLU. All of them were with sigmoid or or TANH was there. TANH we were using. We didn't know about ReLU. So anyway, all of these, for example, here is a problem where we generated the boundaries. The neural network was used. This red and blue classification problem in 2 dimensions. Red line is decision boundary, y equal to 0.5 for the 0.5, the network. And that is made up of dash blue. There is y is the output. Z's are the intermediate values. 2 hidden units are the dashed blue lines. Those together form that. Green line. This green line is the optimal decision boundary. So this blue was generated from a normal distribution, or some distribution was used to generate it. Reds were used with another distribution to generate them. If you know the 2 probability distributions, one can directly plug them into Bayes' rule and figure out at what values the probability of the 2 classes, a posteriori probability, are the same. P of W1 and P of W, or P of C1 equal to P of C2 equal to 1/2. And that optimal boundaries is green line. The neural network is asked to figure out what is the boundary given only these samples. And so it figured out this red line, which is not quite accurate, but that's because we don't have a very large number of samples. And that boundary in turn was a combination of this blue red dotted line and this blue dotted line. Weighted together, they form this line. Isn't that interesting? 2 linear classifiers form a nonlinear classifier. Okay. Oh, there's something about weight space symmetry is not terribly important. Fully connected network. It's all these 2 slides are saying is it's possible to get 2 different neural networks or infinite number of neural networks to solve the same problem. Isn't that interesting? There's not one solution. You can have, because you can change the values of the inputs, weights here and there and so on, and end up with same function being calculated. It's called weight space symmetries. So mathematically, there's an interesting thing that you can have many solutions to the same problem. That's it. Okay, timing became just right. All right, I'm going to close at this point.